Gracias, Manuel. Sin duda, una ponencia interesante. A continuación nos sigue Silvia Franceschi, de Hydrologis Italia, que nos va a hablar de algo que está actualmente muy de moda, que son los drones. Va a hablar en una ponencia sobre la planificación de rutas, dependiendo de la morfología del perfil sobre el que se va a trabajar y cómo ha trabajado ello, cómo ha vinculado ello, los estudios que ha hecho y cómo ha trabajado sobre gvSIG. Cuando quieras.
Gracias. Buenos días. I'm Silvia Franceschi, and I come from Italy, from Hydrologis, that is a small engineering company placed in the north of Italy, and it is part of the gvSIG association. In this presentation, I will show you an example of the tools we developed for planning complex flight plans for drones, where the morphology and obstacles and stuff like that have to be considered for a planning. So what are drones? Many of you maybe already know, but drones are unmanned aerial vehicles. They are remotely controlled flying vehicles, and they fly automatically through a software-controlled flight plan integrated in the system and communicating with the mountain GPS. Often the drones are associated with military use, but they have many other applications, especially in environmental monitoring, search and research, precision agriculture, forest fires, and traffic monitoring. Most of these applications of drones, of monitor with drones, are made by installing a camera on the drones and making aerial photographic or videography. If more than one camera is installed, or if you use some ground control point, it is possible to generate from the images also the point clouds with the elevation associated, and therefore generate digital terrain model and digital surface model. This is an example of the mounting cameras on a drones and survey. Many other applications recently use also thermal cameras mounted on drones to discover objects, persons, and animals in forests because of their different temperature, or to do surveys of solar panels to find the leakages or so on, and to find loss of energies in buildings, or again for fire mapping. In general, it is possible to install on a drone almost every type of sensor that is limited in dimension and in weight. Recent applications also use LiDAR mounted on drones, and also special objects that can be mounted on the drones and used to, for example, in this case, to diffuse components for agriculture. Drones are usually related, when one speaks with drones, you usually have to take in account also the regulation on drones. That is a bit different from a country to another one, but more or less they have same indication. So the drone must stay within the operator line of sight. It is not possible to fly over a maximum height from the terrain. It is not possible to fly within the distance of, for example, in Italy, 5 kilometers from airport and air traffic. And in general, it is prohibited to fly over defined zones that are populated zones, zones with privacy restrictions, or zones with particular emissions. Piloting a drone can be different. It can be fully automatic, partially automatic with the flying automatic and takeoff and landing manual, or complete manual. When one fly automatic, the flight plans are generated in general with external software and sent to the drone. And this flight plan might consider the legislation rules, the morphology of the terrain, the slope, because one has to maintain the same distance or the maximum, not to go over the maximum distance from the terrain, and then the presence of obstacles and also the specific needs of the sensors that is mounted for the survey. For this reason, taking account of all this stuff, we developed a set of GIS tools to generate the flight plans for drones, in particular for two types of surveys, photogrammetry and magnetism. The tools are completely integrated in gvSIG 2.3, and they allow the user to use geospatial supported data types, define and edit geometries and attributes inside these the layers, interact between the tools and the loaded layers. The results are automatically visualized in the view, the gvSIG view, so it is possible for the user to check and verify if they are coherent with the plan. And finally, we generate a flight plan in WPL format, which is ready to be sent to the drone for the flight. The three main tools, the three main modules of these tools follow this workflow. So first of all, we have to create the project files where the user can define the parameters and the geometries. To do this, the user can load in gvSIG other GIS, all the GIS supported data that can help the user to insert all the required information. Then, starting from this information, we generate the flight lines, that is the general route of the plan, and this can be verified by the user, modified, and finally, when it goes well for the user, we generate from these flight lines the flight plan, and this flight plan can be sent directly to the drone. So let's see these tools. When we developed a plugin for gvSIG, and this adds a new menu item here that is called Drone Planner with the three main entries that correspond to the three main modules of the tools. The first one is create the project files, then generate the flight lines, and generate the flight plans. First of all, we have to create the project files. When selecting this first entry of the Drone Planner menu, create project file, our tools create a new project in gvSIG with a new view for the data, and create also the spatial layers, definitely on your PC, with specific geometry types and attributes to be filled by the user to use the rest of the tools. This is a 5-step procedure. First of all, the user has to define the path where to store the data, define the spatial projection, and select the project type. Actually, we support two types of project files, photogrammetry and magnetism, but it is possible to extend these tools to other type of surveys. And then there is the possibility to define the general parameters for the flight. Important parameters are this one, the follow terrain, for example. That is the option that gives the possibility to maintain always the same distance from the terrain, and so considering the changing morphology of the terrain provided by the user by a digital elevation model. Then it is possible to set the flight time corresponding to the time of duration of the batteries of the drone, and also an attribute that is called delta elevation, that is the attribute, the threshold that we use to define that there is a change in the morphology or there is an obstacle to overflow. So we change the elevation also of the drone. And then the user must specify the specific parameters for the project type. For example, for the magnetism, it is possible to specify the altitude, the distance of the flight line from the borders, and the distances between the flight lines. In case of the photogrammetry, we specify all this stuff, the altitude, the overlapping of each picture, considering also the parameters of the camera. So the type of the camera, the image width at the terrain, and this image width at the terrain depends on the flying altitude. When the user defines all these parameters, in case of photogrammetry, we give also an estimation of the precision in the three main directions. So when, if you go on and select OK, the project layers are created in the new view of gvSIG, and these layers are a layer of obstruction, a layer of takeoff points, a layer of waypoints, a layer for the flight plan, a layer for the flight lines, layer for starting line, and flying region. In the same view, it is also possible to load all the data that the user needs to use for defining the parameters, and in particular, it is required to load a digital terrain model containing the elevation of the terrain that are used for all the elaboration depending on the elevation that we have inside the modules. So let's start. For the starting point is defining the flying region. So the user has to edit manually the layer of the flight region, inserting a polygon with the flying area, the area of the survey. Then we need a starting line. This starting line is defined as, this starting line allows us to define the starting point, so the first point of the starting line, and the main direction of the flight line. In this starting line, we copy automatically, the tools copy automatically all the parameters of the survey, the parameters of the flight, and also the parameter of the project, the specific parameters of the project. So it is also possible then to edit this parameter for the user from the attribute table. It is also possible to insert obstacles, and the only attribute needed for obstacles is the height over the terrain. So we know that if we can overflow, and otherwise we increase the elevation of the drone. And from this data we can generate the flight line. The flight line is definitely only the general route of the flight, and it contains some attributes, important attributes that the user can validate in the attribute table. So from this starting line, it is important that the user validate it and eventually modify it, or modify the starting line and regenerate it. To go on to generate the flight plans, we have to consider if there are takeoff points, if the user defines some takeoff points or not. if no takeoff points are specified in the layer, so we consider a unique takeoff point for all the flights at the first point of the flying line. If one or more takeoff points are specified in the layer of takeoff points, we consider each of these takeoff points, and we generate 2 flights in the 2 opposite directions from the takeoff point on the flying line. It is very easy. So, for example, this one is already the flight plan. The flight plan is a set of waypoints. So it's a set of points, definitely, on the flying line. In this case, no takeoff points were specified in the takeoff point layer, so we consider the nearest point on the survey area as the landing point, and this area, for example, is covered by two different flights, but starting all from the same takeoff point, that is this one. The first flight does this route, and then comes back to the takeoff point, and the second one starts from the takeoff point, comes here, do the route, and then comes back. All this information about the timing, the velocity, and the elevation of the drone are contained in the attribute table of the flight plan layer. This is the case where a takeoff point is specified by the user, and it is here, for example, in the middle, at the middle of the area. So we generate 2 different flights, also in this case. One goes from the nearest point on the flight line in these directions and arrives here, and then comes back to the takeoff point. And the second one goes forward and then comes back. Also, in this case, you have all the information contained in the attribute table. If there are obstacles, as you see here, we don't change the flight line, but we have
3 minutes.
We have to change the elevation. So there are some more waypoints specified, as you can see, over the obstacles. And here also is the option with the specified takeoff point. So definitely the flight line, the flight plan is a set of waypoints. As you can see here, the waypoints are put where there is a changing in direction, when there is a changing in the elevation, and if there is the need for the instrumentation mounted to have a triggering point. So we can insert also this triggering point. The information that we have here in the shapefile are also saved in a WPL file, and this WPL file can be sent directly to the drone and contains, in fact, the flight plan. So this is all, and thanks for your attention.